Okay, so let's work through some examples in 7.2 and put a little bit more meat on the bones of the skeleton of Laplace transform that we talked about. In 7.1, we kind of introduced some difficult situations that we would run into if we had piecewise defined functions and doing normal differential equations. So we introduced this idea that we might be able to do a transformation to transform piecewise functions or any functions into something that is a little bit easier to work with than our normal techniques. So remember we defined that the Laplace transform f of s, which is a transform of little f of t, is given by the integral from 0 to infinity from e to the negative st times f of t dt, where f of t, excuse me, is the function we're transforming. So we could denote this f of s, or we could denote this L of f. So the Laplace transform of f. So let's start out by illustrating this using the function f of t equals 1. So our transform of this function will be the integral from 0 to infinity of negative st times f of t, which is 1. So just 1 times dt. So to integrate this, to get our antiderivative, this is e to the u du, which integrates into e to the u. But we need to make this fit our u. So if u is negative st, with t being the variable, the derivative of that is negative s. So we need a negative s here and a 1 over negative s out front. So now this is e to the u, and that's du. So when we integrate that, we have our negative 1 over s out front. The integral of e to the u is e to the u, and we're evaluating that from 0 to infinity. Now remember, this is an improper integral. So really when we're integrating to infinity, we're taking the limit is n goes to infinity, and we're replacing infinity with n. So we're calling that n, and we're going to plug n for t, 0 n for t, and wherever we have an n, we're going to let that go to infinity. So I may be a little lax with my notation here and just use infinity instead. But just think about when we're plugging infinity in, we're really talking about what is the function approaching as we go to infinity. So what is the limit? So if we plug in an infinity for t, we get negative 1 over s e to the negative s times infinity would be negative infinity minus negative 1 over s times e to the, if we plug a 0 in, we get 0. E to the negative infinity, as that goes to infinity, this gets smaller and smaller and smaller, so that goes to 0. So that's 0. Minus a negative makes a positive. E to the 0 is 1, so we end up with just 1 over s. So that's the transformation of the constant 1 into the domain of s. So let's look at another example. Let's look at transforming e to the 3t and transforming it into the Laplace transform, so into s. So we use our formula, 0 to infinity, e to the negative st times e to the 3t dt. We're multiplying with like bases here, so we can combine the exponents. So we combine those exponents, and we negative st plus 3, or we could call that negative s plus 3 t dt. So we just need to do a u du fit. If this is our exponent, then the derivative of the exponent would be negative s plus 3. So we would need a negative s plus 3 here on bottom. So we have, we could call that 3 minus s if we want. This is the integral of e to the u, that's du. So that's e to the negative s plus 3 t. And we're evaluating that from 0 to infinity. So if we substitute in our infinity, we have 3 minus s. We're putting infinity in for t. So that's e to the negative s plus 3 times infinity. And then minus 1 over 3 minus s. And we're putting a 0 in. So if we put a 0 in, we have e to the 0. So now let's think about what we have here. If s is smaller than 3, so if we have numbers like 1 or 2 here, then we have a positive number times infinity, which is going to positive infinity, and that's going to get really big. But if s is bigger than 3, so if s is 4, 5, 6, this is going to be negative. So as long as s is larger than 3, this is going to go to negative infinity. E to the negative infinity is 0. So that's going to go away as long as s is bigger than 3. So what we would have left, all right, sorry for the interruption, I'd gotten a phone call. So for this part, is, since the s is greater, if s is greater than 3, we said that part goes to 0. So we can distribute this negative, and we end up with 1 over s minus 3. E to the 0 goes to 1. So anything times 1 is itself. So that's what we get when we take the transform of e to the 3t. And it turns out that depending on what that number is, if that was 4, if that was 9, if that was 11, if we're transforming e to any number times t, the transform is 1 over s minus that number. Okay, so that gets us through a couple of transformations that were just standard functions, but one of the benefits of doing the Laplace is for piecewise functions. So let's look at this one. If we have the function that's a piecewise function that's 2 from 0 to 5, so a constant, and it's 0 from 5 to 10. And I tell you what, let's move the 2 down. It's not going to let me. Let's do the 2 down here at the end when t is greater than 10. And let's do sine 2t here. So when we do our transformation, we have the integral from 0 to infinity of e to the negative st of f of t dt. So our number line is split up into 3 segments. So we have the integral from 0 to 5 of e to the negative st sine 2t plus the integral from 5 to 10 e to the negative st times 0 dt plus the integral from 2 to infinity e to the negative st times 2 dt. So we just need to do each of these individually. So let's come back, let's do this one lastly. The middle one, anything times 0 is 0. Whether we put the 0 inside or outside, 0 times anything is 0. So that one's gone. On this last one, let's move the 2 into the front. Let's leave everything else inside. This is going to be e to the u du. So the derivative of u is negative s times dt. So we need a negative s there. We need a negative s on bottom there. And then we would integrate that. So we could call that 2 over negative s. The integral of e to the u du is e to the u. And we're going to evaluate that from 2 to infinity. So we have 2 to the negative s out front. If we insert infinity, e to the negative infinity times s, as long as s is positive, infinity times a positive number is infinity. Remember, we're really taking the limit as that goes to infinity. But then if we put a 2 in, we have e to the negative s times 2, or negative 2s. That goes to 0. We can combine these two negatives. That will make a positive. So we end up with 2 times e to the negative 2s over s. Or we can move that down as e to the 2s on bottom. So if that's gone, we're left with that times that. So 2 on top, s on bottom, the negatives cancel. So then if we come back here, there's a formula to do this integration. If we look in our formula, in our table, there's a formula that says if we have e to the au sine nu du, that integrates into e to the au times a sine nu minus n cosine nu over a squared plus n squared. So what we have is e to the negative s t. We have sine 2t dt. So our a is, so our variable, this is u, that's u, that's u. So our variable is t, so t, t, and t. So a is negative s, n is 2. So this is what we get when we integrate that. We get e to the a e to the a t times a sine n t minus n cosine n t over a squared. So if we square a, negative s times negative s is s squared plus n squared. So 2 squared is 4. So that's what we get when we integrate that. And then we're going to evaluate that from 0 to infinity. So it turns out if t goes to infinity, and you could do this using L'Hopital's rule or different ways you could evaluate that limit. But if t goes to infinity, it turns out that goes to 0. So we're going to have 0 minus, if we put in a 0 for t, e to the 0 is 1. So we're going to have 1. In the parentheses, if t is 0, sine of 0 is 0, so that's gone. Cosine of 0 is 1, so we're going to have negative 2 over s squared plus 4. So we're going to end up with 2 over s squared plus 4. 2 over s squared plus 4. So that's what we get for our transformation. Even though we had a piecewise defined function that had 3 different parts to it, we end up with a transformation that is not piecewise. It's just has a standard domain. Let's make a few more observations about this. So if we need to do the transformation and we have functions added together, could be 2, could be 3, however many, then we're able to take the transform of each individual piece. In a way we did that on the previous example except the ones that we did in the previous example existed for different values of t. But these could exist for the same values of x instead of different values, but we just take their transforms separately. The transform of the first part and the transform of the second part and add them together. The same thing is true if we have a coefficient. If we know what the transform of f is, we take the transform of it and it gets multiplied by that constant. So the same linear properties that we've used for derivatives, for integrals, for limits, all of that, those apply to these transforms. So just like when we did derivatives way back in Cal 1, we did it the long way, and then we found out there are short ways to do that. There's a table on page 356. There's a brief table of transformations. We've seen that if we have 1, the constant 1, that transforms into 1 over s, as long as s is greater than 0. If we have e to a power, e to the at, that transforms into 1 over s minus that coefficient, as long as s is greater than that number. If we have t to a power, where n is an integer, that transforms into n factorial over s to the n plus 1, where s is greater than 0. If we have sine bt, that transforms into b over s squared plus b squared. S is greater than 0. If we have cosine, that transforms into s over s squared plus b squared, as long as s is greater than 0. If we have e t times t to the n, that transforms into n factorial over s minus a to the n plus 1 power. And that's true as long as s is greater than a. If we have e to the at times sine bt, that transforms into b over s minus a squared plus b squared. S has to be bigger than a. And if we have e to the at cosine, that transforms into s minus a over s minus a squared plus b squared with the same restriction. So here's just a list of some basic transformations. So if we're given functions that are related to any of those, if we can write it as a sum or difference, maybe we have to pull some constants out, then we're able to do the transformations just using the table. So let's suppose we have 4 plus 2e to the 3t plus cosine 5t. And let's suppose we want to transform that. So we're going to transform 4, and we're going to transform 2e to the 3t, and we're going to transform cosine 5t. 4 is just a constant, so we could put it in the front, and that's equivalent to 4 times the transform of 1 earlier we saw to be 1 over s. Here, 2 is a coefficient, so we can bring the 2 out front, and we can transform e to the 3t. So e to the 3t transforms to 1 over s minus 3. That's our a, our coefficient of t, so it's s minus that number. And then the transform of cosine 5t is s over s squared plus that coefficient 5 squared. So that's our transformation. So that's way quicker than having to integrate those separately and then take the limits of those separately. So there's the rest of this section is just mentioning existence, when this works, when it doesn't. So there's a definition of being piecewise continuous, piecewise continuity. And if we have some piecewise function, and I'm just going to call this f1, f2, f3, and then we have different sections. So maybe t is between 0 and 3, and then t is between 3 and 5, and then t is bigger than 5. If f1 is continuous in its interval, and if f2 is continuous in its interval, and if f3 is continuous in its interval, then this is referred to as being piecewise continuous. Now, when we talked about continuity in calculus, for the function itself to be continuous, then these functions had to be equal where it transitioned from one function to the next at the boundaries. So this function and this function had to equal at 3. These functions had to equal at 5. But for piecewise continuity, we don't have to include that. As long as each function independently is continuous on its given interval, then we have piecewise continuity. And that's going to be important because when we do our transformation and we change this from a piecewise function to something that's no longer piecewise, we do have to have that continuity in order for that transformation to apply. One of the comments, and this comes from the book, they mentioned that if we have a finite interval, if our interval goes, let's suppose, say, from 0 to 13, as long as it's piecewise continuous in those intervals, then this is going to guarantee to be integrable. All that means is that if this is continuous, we could use the long method, e to the negative st times f1 dt, to find out what that transforms into, and then the same thing for this and the same thing for this. Where we run into trouble is when we're going to infinity. Sometimes when we go to infinity, we might have a function that when we try to do the transformation, when we try to do 0 to infinity e to the negative st of ft dt, that when we go to infinity, that it diverges. So what if we diverge as we approach infinity? So if it diverges, then that transformation doesn't exist in that particular region. So they define what's referred to as exponential order. And they call it exponential order alpha. So it says a function f of t is of exponential order alpha if for every positive constant, if for t and m that are positive, then our function, the absolute value of our function, is less than or equal to m times e to the alpha t for t greater than or equal to t. So that looks weird, messy, and confusing, but it just says as long as our function is not bigger than this for some certain values of m, then we're of exponential order. But if we're not of exponential order, then this is not a true statement. So an example of when we are of exponential order, if we have f of t equals e to the 3t sine t, the exponential order alpha on it turns out to be not 5, but 3. Why is that? Our function, e to the, keep on writing 5, 3t sine t, that's less than or equal to e to the 3t for all values of t. Why is that? Sine is at most 1. So when sine is 1, these two sides are equal. Sine, the smallest value for sine is -1. Take the absolute value of that, we would have e to the 3t. Any other value, sine is going to be a decimal between 0 and 1. So this would be smaller than e to the 3t. So in this case, I mean, we could say 4, we could say 5, and that would always be a true statement. But the smallest number we could have here, this is alpha. Back to here, alpha is the exponent here. So f of t is our function. So we're comparing that to m. We're just randomly using 1 for m, e alpha t. So since there is a value here such that this is always lower than whatever that smallest value is, that is our exponential order. Now if we look at another example, let's see if I can find one. If we looked at e to the t squared over e to the alpha t, I think that's the one I want to do. Let me check. Okay, so I was jumping ahead of myself a little bit. So if we look at the function e to the t squared, this is not of exponential order. Not exponential order. Why is that? So if we compare our function e to the t squared, let's see if that's less than or equal to m times e to the alpha t. Divide both sides by e to the alpha t. We're going to, for simplicity's sake, drop the absolute value. So here m is a constant. Remember, m is a positive constant. So in order for e to the t squared to be of exponential order, then when we rearrange this, there has to be some constant so that when t goes to infinity, that this limit exists, and not only does it exist, it's some constant, it's not infinite. So we could use L'Hopital's rule or other things to denote that, hey, this does not go to a particular constant. For this particular function, the numerator is going to grow faster than the denominator. It might not be larger to begin with because of this alpha, but once we get into large enough numbers, t squared is going to be significantly larger than t to the first. So that does not exist. That doesn't work. Hence, that's not of exponential order. So they have a, the last thing I want to mention probably in here is this theorem that they give us. And they say if we have a function f of t on the that's a piecewise function on this interval, if it's of exponential order, then the transform exists. So if f of t is of exponential order alpha, then the transformation does exist. Otherwise, it may not exist.